This is problem 40 from chapter 11, Intermolecular Forces, Liquids and Solids. And the compound is a fluorocarbon with a normal boiling point of 47.6 degrees Celsius. And the specific heats for the fluorocarbon are given to us for both the liquid and the gas phase. And we are also given the delta H vaporization for the compound. And we are asked to calculate the heat required to convert 25 grams of that substance from its liquid state at 5 degrees Celsius to its gaseous state at 82 degrees Celsius. So the easiest way to break this down and look at this kind of a problem is to draw a heating or cooling curve, which we will do on the next page. So any heating or cooling curve is going to look pretty much the same way in terms of having our temperature on the y-axis and our energy or heat being added to the system on the x-axis. And it's always going to show the different segments in this way, okay? This first segment, which is going to go from here to here, is where the substance is going to be in its solid state, where the molecules or the atoms are packed very closely together and very rigid, okay? And this second segment of this graph is going to be where a phase change happens, where the solid goes into the liquid phase. Now, once all of the compound has made its way into the liquid phase, then we would move up to the next section of the graph. So once we go into the liquid phase, now the atoms are greater kinetic energy, moving a little bit further apart from one another. In the liquid phase, basically, they are close enough where they slide past each other and are able to flow. So once we have our substance in the liquid phase, as we continue to add heat energy to the system, we're going to go through another phase change, which is going to be our fourth section. And a fourth section of the graph, and in this segment we're going to go from a liquid to a gas. So wherever you see a flat line on the heating or cooling curve, you're going to be going through the substance will be going through a phase change, okay? And during a phase change, as you can see, the temperature does not increase. The temperature holds steady until the substance is completely converted over into the next phase. So once we've gotten to this point of reaching, all of our substance has now reached the gas phase, the temperature will again begin to rise, and now the gas molecules, even more kinetic energy, so much further away from one another in the gas phase. Now, in order to solve a problem like this, the first thing you want to do, until you get used to working these types of problems in any case, is to draw your heating curve and plug in your boiling point and your freezing or melting point. Now, in this problem, we are given a boiling point of 47.6 degrees Celsius. So I'm going to plug that in right about there, okay? So that's going to be 47.6 degrees Celsius. And our freezing or melting point is not actually given to us in this problem. But the problem does tell us that we are going from the liquid phase at 5 degrees Celsius to the gas phase at 82. Now, if I know my boiling point is 46, and we're going as high as 82 degrees Celsius, well, I know that's going to be somewhere above the boiling point. So I'll just make a little tick mark right there. And the point that we're starting out from is at 5 degrees Celsius. I don't know where that is in relation to the melting point, but it really doesn't matter because the problem tells me that it is a liquid. So I know that if it is a liquid, it's going to be someplace above the melting point. So I'm just going to arbitrarily put that 5 degrees Celsius right there, okay? Because I know if I go across here, I'm in the liquid phase, okay? So what we will do to figure out how we're going to get from 5 degrees Celsius up to our peak temperature of 82 degrees is to take each section of the graph and calculate the enthalpy change for each section of the graph. Once we know the enthalpy amount for each section, then we can add the sections together, we can add the enthalpies together, and we will end up with the total heat required to go from 5 degrees to 82 degrees. So our first step is going to calculate the heat, or the Q, from 5 degrees up to here, which is the boiling point. That's going to be the point at which our substance changes from a liquid to a gas. So I'm going to move over to the next page. Before I do that, take note that as we are adding heat to the system, as it's in the liquid phase, the temperature is increasing. So we have a change in temperature. Wherever you have a change in temperature, you'll want to use the formula Q equals mc delta T, where m is the mass of the substance, C is the specific heat, and your change in temperature is going to be T final Now my freezing point or melting point is always going to be right there at the point where we have that first level section of the graph. And my boiling point is always going to be where we have that second section of the graph that is flat, where we said that we were going to be going, the substance would be going through a phase change. Now, in this problem, I am given the boiling point of 47.6 degrees Celsius. I'm not given a freezing point, but the problem does tell me that we're asked to calculate the heat required to convert the 25 grams of the fluorocarbon from a liquid at 5 degrees Celsius to a gas at 82 degrees Celsius. So I know 82 is going to be someplace up here. I'm arbitrarily just going to put it up there. I just know that it's a gas. It's someplace up on that last section of the graph, and it's someplace above the boiling point. And it also tells me that it is a liquid at 5 degrees Celsius. So I'm going to arbitrarily put 5 degrees Celsius on this y-axis someplace where I know the substance is going to be a liquid. So let's just stick it right there. So 5. Okay? So we're going to go from someplace around here at 5 degrees Celsius in the liquid phase up to the boiling point. And we're going to calculate the amount of energy required to make that change, okay? Now, there is an increase in temperature in this part of the graph. So the formula that we would use would be Q equals mc delta T. Actually, I think what I'll do is just move that right here. We'll use Q equals mc delta T. Then, after we've done that, we're going to find out how much energy is going to go into the phase change to make the substance go from the liquid to the gas phase. Now, during a phase change, all of the energy that's being put into the system is going into making the phase change happen. So there is no temperature increase during this change. So what we're going to do then is use the enthalpy of vaporization, or the delta H vaporization, to calculate how much energy is going into the phase change. And then the next step will be to have the substance now turning into the gas phase to calculate the amount of heat energy that goes into the system to go from the boiling point up to the peak temperature that's given to us. So in this case, the third step is going to be to calculate that leg of the graph, where again we have a temperature change, so we will use Q equals MC delta T. And then to finish out the problem, what we'll do is we'll add the energy change from here to here to here. We'll add those three together, and we will get the final answer for the amount of energy needed to go from 5 degrees Celsius to 82 degrees Celsius. So we'll begin by calculating the first step in the process, where we have our substance, which is starting at 5 degrees Celsius and going up to the boiling point at 47.6 degrees Celsius. Since we have a temperature change, we're going to use Q equals MC delta T. Now, the mass that we are given is 25 grams. The specific heat that we're given, and you have to be really careful when you're using these formulas, and as with everything that you do in chemistry, in terms of making sure what you're using is in the correct state, making sure that your units line up, and so forth. So we want to use specific heat in the liquid phase right now, and the specific heat in the liquid phase is 0.91. And the units are joules per gram, Kelvin. And our change in temperature, and in terms of the units here, we do have grams, we do have grams, and we have Kelvin. Obviously, the Kelvin scale is based on the Celsius scale, so the change in temperature will be the same regardless whether you were using units Kelvin or Celsius. And the change in temperature that we're looking at is going from initial temperature of 5 to a final temperature of 47.6. And our change in temperature is always final minus initial, T final minus T initial. That gives us a change in temperature of 42.6 degrees Celsius. Now, when I multiply everything, my units, take a look at that. I have grams here, which will cancel out with grams in the denominator here. I have, I said that I could use Celsius and Kelvin interchangeably here because we're talking about the change in temperature. So my units Kelvin also will cancel out, and my final answer will be in joules. And so when we multiply across, we get 969.2 joules. Now we're ready to calculate the amount of energy that's going to go into the phase change to change the substance from the liquid phase to the gas phase. So that's going to be our flat part of the graph here. And obviously there's no temperature change, and we said that the amount of energy required to go from the liquid phase to the gas phase is called the delta H vaporization. So what we're going to do is take a look at that. Okay, the delta H vaporization that we're given is 27.49 kilojoules per mole. I don't know how many moles I have, but I know that I have 25 grams of the substance. So I'm going to have to change that from grams to moles. So 25.0 grams has a formula mass of 187.4 grams per 1 mole. That's going to give us 0.133 moles of the compound. Now, if our delta H vaporization is 27.49 kilojoules per 1 mole, and we have 0.133 moles, then that means the energy that's going into converting that 0.133 moles will be 3.66 kilojoules. So our first section to go from here to here required 0.969 kilojoules. Our second section, which took us through the phase change, required 3.66 kilojoules. Now we need to calculate the third section of this particular graph, which is going to take us in the gas phase from the boiling point, 47.6, to the peak temperature that's given, which is 82 degrees. So now again, since there is a temperature change involved, then we will use the formula Q equals MC delta T. So our mass is still 25 grams. Our specific heat that we want to use, now we're in the gas phase, so we have to use the specific heat of the gas. And our specific heat for the gas is 0.67 joules per gram Kelvin. And our delta T, our change in temperature, T final minus T initial for this section of the graph, is going to be our peak of 82 degrees Celsius minus the boiling point of 47.6, which gives us a delta T of 34.4 Kelvin. And when we multiply, I got 576.2 joules, okay? Grams cancel, Kelvin cancel, and we're left with joules, okay? And if I change that to kilojoules, I have 0.567 kilojoules. So there's my third step. And finally, what we'll do is we'll add the 3 steps together for a final answer of 5.21 kilojoules.